All right, so we'll start chapter 2 today. Okay, it's about the application layer. So in the last class, we discussed in brief the protocol layers, right, that we have for data communication over the internet. All right, so let's refresh our memory a little bit. So how many layers do we have? Anyone?
5.
And what are those?
Application,
Network, transport,
physical,
And two more.
the link layer,
Yes.
and the network. Didn't we say that already?
Yeah,
Application, transport, network, link, and physical.
physical layer. Yeah. So when we have a layered service model, then we know that the layers, they provide services to other layers, and also, they use services from other layers. Okay. So today we'll talk about some of the protocols from the application layer, which is the topmost layer in the hierarchy. Okay. And below the application layer, we have the transport layer. So the application layer uses services provided by the transport layer, okay, to provide services to the users, to the applications, right? So in this chapter, we'll look at a few services that are provided by the transport layer as well. Okay, but very briefly, we'll only talk about the services, not in detail how those services are provided. Okay, we'll talk about that in the next chapter when we discuss the transport layer. Okay, so in this chapter, we'll talk about the preambles, okay, basic principles, and then we'll talk about some of the protocols, okay, that support different types of applications, like web applications, and then the HTTP protocol. We'll talk about the protocols for email, SMTP, IMAP, right? POP, post office protocol, different versions of it, and also the DNS, domain name system or service. Then we'll talk about different architectures, network architectures, or to build applications. All right. And we'll also look at an example of socket programming today. All right. And this chapter also has, discussion on video streaming and content distribution, like those for Netflix, okay, Akamai, or any streaming service, how they really work. As long as we know these protocols, it's going to be easy for you to, understand those services or applications. So this is going to be a self-study, okay, this topic. And we'll talk about the rest of the topics, right? Okay. All right. So now today we'll talk about these different paradigms: client server architecture, peer-to-peer architecture. We'll also look at the BitTorrent protocol, how it works, and we'll also look at a bit of socket programming. Yeah, and then if we have time, we'll talk about the HTTP a little bit. Okay, and then in the next class, we'll talk about email protocols, DNS, and the rest of the topics. Now, when it comes to the applications, we have a variety of them, right? Including social media, social networking. Then we have billions of websites, text messaging applications, email, file sharing, then voice applications like VoIP or Skype. We are using Zoom, which is also an application, right? Then we have the searches, search engine, remote login, right? So there are a variety of them. So which one is your favorite? Perhaps not just one, right?
Yeah.
Multiple with applications, right? I don't use social media. Okay. I use emails, Zoom. Okay. I watch a lot of videos on YouTube.
Say YouTube and P2P, probably like two most that I use here in this list.
Okay. Yeah.
Other than like internet search.
ChatGPT. Yes, ChatGPT is also an application, right? Okay. So let's talk about how to create applications from very high level view. Okay, so we know of this architecture, right? This is a network of networks. Here we have N systems, right? We have routers. We have an access network or few access networks here. We have a few network cores as well, right? So definitely to build an application, we need to write code, right? Or we need to write programs. And these application layer applications, right? Or the applications, web applications, they run on the end systems only, right? They don't run on, network core or any of the routers in the network, all right? So these end systems, they actually talk to each other, through different apps, right? So we have network applications and we have communication between them, right? Okay, now whenever you search for, let's say, a website or try to browse a website, you use an application like an web browser, right? So web browser is an application. Then there is a counterpart of this web browser in the servers, right? And like I said, the network core devices like the routers or the switches, they don't need to run any applications because directly they do not provide services to the application layer, right? The network layer provides services to the transport layer, not to the application layer, okay? So they don't need to run any applications at all, right? And also it also makes sense to run these applications on the end systems only, like mobile phones or a laptop, right? Or even in the servers. It gives us much more flexibility. And yeah, I mean, if you look at the network core, oftentimes, not many people also have access to the network core, right? So that is another reason why we shouldn't, build applications for the network core. Okay, so now while building an application, okay, for the web or the internet, there are a couple of structures that we can follow. Okay, so during the lecture, if you have any question, please unmute yourself, okay, and speak up. I'm not looking at the chat, all right? So there are a couple of architectures for building network applications or web applications. Okay, one of them is called the server client architecture, okay, which uses a server client paradigm, okay, for the communication, between the applications on the web. So the end systems or end devices or the edge devices, they they can either work as a server or as a client, right? Now, when a device is acting as a server, it will have certain properties, okay? For example, it will have to be always running, okay? Or it is expected that the server will be always running. And that is the case, right? On the internet, all the websites that we have, we can access them anytime we want. So it means that there is a server component for that application, okay, or website, which is always running. Okay, so there is always running host or a server, okay? And it will also have to have a permanent IP address. It cannot keep changing the IP address, okay? If it does that, then it will be too much work for the DNS. We type facebook.com, right? But the DNS has to resolve the IP address for facebook.com, right? If there is a permanent IP address for facebook.com, then it's easier for the DNS to resolve the IP address, right? But if facebook.com keeps changing its server IP addresses, then, you know, it will be difficult, okay? Every time you try to log on to Facebook, it will take long time for you to, be connected to the server. And these servers, they are often placed in data centers. Okay, and they are very powerful machines. They are always running, so they are connected to a power source, right? They don't run on batteries. Okay. And they're placed in data centers for scaling purposes, right? Facebook, Google, Microsoft, everyone has their data centers. And within a single data center, they can have, from thousands to hundreds of thousands servers. All right. So that's more or less the characteristics of a server. Always running, have a permanent IP address, and it's very powerful. Okay. And oftentimes it's not just one machine that acts as a server, it's a collection of machines or computers that act as a server. For Facebook, for Google, or for any big companies, that is the case. All right. So when you make a request, one of the machines from the data center will serve your request. Okay. All right. On the other hand, the clients, they don't have to be always running. Okay. They can come and go from the network, to and from the network. Okay. And they communicate with the servers, right? Your web browser communicates with the server to, get you all the information that you request, right? And the clients, they can have dynamic IP addresses. Okay. And that is the case. If you look at or think about your mobile phone, when you are connected to your home Wi-Fi, you get one IP address. When you go to the campus, right, and connect to QC Wi-Fi, you get another IP address. But still, you can visit the same websites, right, that you have visited from home, okay, and so on. And in this architecture, server client architecture, the clients, they do not talk to each other directly. Okay. They can only talk to the server. And in a case, if two clients need to talk to each other, then that will be through the servers. Okay. Now, if there is a messaging app, then it feels like two different clients are talking to each other directly, but that is not the case. Whenever you send a message, it first goes to the server, and then from that server, the message is forwarded to the recipient, right? Which is also a client. Okay. Okay, so yeah, for servers, they're always running static or fixed IP address. For clients, they can be, intermittently connected. Okay, they will have dynamic IP addresses and they will not talk to each other directly. Okay, so that's the essence of server client paradigm. Now, when you will do your project, the first thing that you'll have to do is choose an architecture. Okay, whether you are going to use the server client architecture or a different one, okay, that we are going to discuss in a moment. So the applications that use HTTP, okay, or IMAP for email, okay, or FTP for file transfer, they typically use the server client architecture. Okay, any question about this architecture? Anyone?
First, I got a question.
Yeah.
So as we speak right now, right, via Zoom, so that means we're not directly speaking with each other. We're talking to the server, and then the server is giving us the connection.
Yes.
Okay.
So Zoom has an HTTP version of it, okay? And it also may have a proprietary protocol as well running. So whenever you use the Zoom from the browser, it is actually using the HTTP protocol and probably few other protocols as well. Similarly, it goes to the email clients as well. If you have an email client installed, okay, like the Mail app on macOS, okay, or Outlook, okay, those email clients, they also use client server architecture, but they run, let's say, this protocol, okay, this application layer protocol, IMAP. Now, when you log on to your Gmail account from a browser, you're not using the email client on a browser, at that time, it typically uses the HTTP protocol, but still it always uses the server client paradigm, okay? For email clients, there is no peer-to-peer protocol that we are gonna discuss in the next slide. Now it happens so fast, but still there is a delay, right? You're definitely getting what I'm saying after a few seconds, okay? Or let's say hundreds of milliseconds, not instantly. Well, even if you were, sitting in front of me, it would take some time for the sound voice to travel to your eardrums, right? But it's all right for us as long as the delay is around 1 second, 2 second, we can call it real time. All right. And these applications, they use cloud architecture, right? And if some company like Amazon through Amazon AWS or Microsoft through Azure, they have data centers, in every big cities or in many places of the world, okay? So it will choose a server, okay, that is perhaps the closest to both the sender and the recipient, okay, to minimize the delay. All right. So the next architecture is called the peer-to-peer architecture, where the end systems, they are called peers. Okay. And in this architecture, there is no notion of server, no notion of a server device. Okay. And it's important. There is no notion of a server device. All right. So all the clients, I mean, we can call them clients or peers, okay? In this case, it would make sense to call them peers, okay? The peers, they talk to each other directly. All right, so it means that, and also it has this they can come and go. They don't have to be always there in the network. Usually in a P2P network, whenever a peer needs some service, okay, it will come and join the network and request for service, okay? And also, if a peer has, something to offer to the other peers, then they will come and join the network and will probably stay there for longer, okay, compared to the others who simply come to get services, okay? So in peer-to-peer architecture, there is no notion of servers. So the peers, they get and provide services, okay? And it is self-scalable, okay? Any number of peers can create a peer-to-peer architecture. Okay? And they also have the IP addresses can change. So the management becomes really complex for a peer-to-peer network. Okay? It's not easy. It's a complicated protocol in terms of management, since they can come and go, okay, or they can have different IP addresses across different sessions, which is really difficult to deal with. All right, let's say you were getting some service from someone, okay, and then at some point you went idle and later you need the service again and is trying to get the service, but it may be the case that the other peer is not in the network. And you'll never know when that peer is gonna come back to the network again, okay? All right. So usually when you have some application to build and the, participating peers, then you can perhaps manage them easily, okay? But if you are a part of a peer-to-peer network where nobody knows anyone, okay, and they don't also have contacts in any other way, then it can be really difficult, okay, to get in any service or to even provide any service. Okay, in that case, maybe there will be some third party who will be managing everything, okay, but that third party will not be regarded as a server, because that party will not actually provide any service, useful service to the peers, okay? All right, questions. Now, examples of P2P architecture, like peer-to-peer file sharing, including BitTorrent or something else, okay? So BitTorrent, it's a nice protocol, okay? But people these days, they use this protocol to, share files that shouldn't be shared. Okay, so that's the main issue, but the protocol itself is all right, okay? It has no issues, and it's a very good one, but people use it for other purposes. And that is the case. We can build applications and we cannot restrict people to use it in a certain way. Okay, that's the problem. All right, questions about P2P architecture.
So, Professor, what I got from this, what I understood is like, it's basically for uploading and downloading files. That's what peer-to-peer architecture means.
Uploading and downloading, those are the services, right? So yeah, you can create a peer-to-peer application using which you can provide uploading and downloading services, but it can be used in many other applications as well, which may not involve uploading or downloading. If you think about the Bluetooth network, okay, you can connect, let's say 5, 6, 7 Bluetooth devices together. And Bluetooth will create a peer-to-peer network for you. It will not create a server client architecture based network. Okay. Now using Bluetooth, it's not about only transferring files, right? You can create a even smart home application, right? sending commands to do some actuation, and so on. All right. Then if you know about the Wi-Fi Direct, so there is something called an Wi-Fi Direct. Wi-Fi is server client based architecture. Okay. The typical Wi-Fi one where you connect your mobile phone to the access point. All right. It's a server client architecture because the access point here is doing providing you a lot of services, not only letting you access the internet, it's doing a lot of other things as well. Okay. And also if you need to, connect two different mobile phones through your Wi-Fi router, then, everything will go through the router before it goes to the other device, right? These days, if your TV is or any monitor is connected to the Wi-Fi, you can simply use that device as an extended monitor, right? Okay. So I can connect my laptop to my TV and use the TV as a monitor through my Wi-Fi network. Okay, that will be a server client architecture. All right. But there is a version of Wi-Fi which is called the Wi-Fi Direct, where you can actually just give me 1 second. Yeah, so through Wi-Fi Direct, you can directly connect your mobile phones. In that case, you do not have to, use the Wi-Fi access point. Anyone here ever used Wi-Fi Direct?
No.
No.
Don't think so.
Okay. So yeah, back in the days, we used to use Wi-Fi Direct a lot. So yeah, I used to work for Samsung. That was in 2013, and I worked on their Bluetooth, NFC, Wi-Fi Direct modules. Okay. So yeah. So I have written code for Wi-Fi Direct in Samsung mobile phones. I was working on Galaxy S4 at that time. What's the current Galaxy version?
Isn't
I
it
think
like
like
12?
S24.
Oh, wow.
Yeah. So in 10 years or so, they came up with so many versions. Yeah. So I was stationed, in South Korea. There is a place called Kumi, which is their headquarters. So yeah, I worked there for a year and 6 months. So 1.5 years. It was fun. I messed up a few times. Okay.
Did you learn some Korean?
Say it again.
Did you learn some Korean?
A little bit, okay, not much. So once I was working on the Wi-Fi module, okay, of Galaxy S4, and we had a Samsung Galaxy Note 1, 2 was just coming up, okay, and also those Galaxy Tabs, all right. So there were some issues and I was fixing the issue for Wi-Fi. I fixed the issue, but I created a new one. Okay, and when I went to the hotel, after the office, then the next day I came to the office, I got like more than 100 emails from all over the world. People are, complaining, hey, this is happening, fix that, All right. So yeah. So we have server client and then we have peer-to-peer architecture, right? Now, we have this notion of two different applications, they're talking to each other, right? But what happens in reality is that the applications, well, they're merely processes, right? From the standpoint of an operating system. And an application, it can run multiple processes, right? And also if you're running multiple applications, then it's definitely multiple processes that you're running, okay? And what is a process? If you have taken the operating systems course, then you know that a process is a program in running, right? All right. So basically, when I say two different applications, they're talking to each other. Actually, their corresponding processes, they are talking to each other. All right. And if you have two different processes that are running within the same machine or under the same operating system, then we have something called an inter-process communication, right? Which is defined by the operating system. But for this network applications, or what happens, the processes, they run on two different machines. So the basic inter-process communication provided by the operating systems is not sufficient, okay? Or in other words, the processes, they talk to each other over the network by exchanging messages, okay? By sending packets of different types. Now, from this point of view, we can say that we have, a client process that initiates the communication or that requests for some services, okay? And we also have server process, okay, that waits to be connected and that also provides services to the client processes, okay? So again, for any application, doesn't matter if it's a server client architecture based or peer-to-peer architecture based. One more time, it doesn't matter if it's a server client based architecture or if it's a peer-to-peer, based architecture. There will always be a client process and a server process, okay? Now, for server client based architecture, we know that client process will be running in the clients and the server process will be running in the servers. It's obvious. But for peer-to-peer network, what happens? Okay, we know that in peer-to-peer network, some peer provides services, some peers get the services. So the peers that are getting the services, they will run the client process or processes, okay, in them. And the peers that are providing services will usually run the server processes, or the processes in the peers that are providing services will be called server processes, okay? So in the peer-to-peer network architecture, we also have the server process, client process paradigms, okay? And I hope this is not confusing to you. So yeah, we know that we have server client architecture, so it makes sense to call those processes server process and client process. But in peer-to-peer network, we also have server processes and client processes. And a single peer, it can run a client process at times. It can also run a server process at times. whenever it is getting some services from other peers, it will run the client process, or that process will be called a client process. Or whenever that same peer is, providing services to other peers, then we'll say that the process is a server process that is running the peer right now. Okay. And this will become more clear when we discuss TCP or even UDP in the next chapter. Okay. All right. Questions? Anyone?
Professor,
Yeah.
so when I connect my device with my car's Bluetooth, right? And I play the music from my phone. So my phone serves as the server and the car is the client.
Yes, perhaps, yes. But it is still a peer-to-peer network.
Okay. So within the peer-to-peer, the phone serves as the server and the car serves as the client.
Well, it may be ambiguous. We have to include the word process. Otherwise, people may, misunderstood it for server client architecture. Right? Does it make sense?
Okay. Yeah. Thank you.
Professor,
Yeah.
a process does not include things I do on my cellular phone that are offline. Like, for example, let's say I'm on airplane mode and I play a game or something, that is not considered a process in this context because it's not accessing any server.
Well, from the standpoint of the operating system, it's the processes that run. So you are, using the airplane mode and you are playing a game or something else, doing something else. So you're running a process, right?
Okay.
From the
Yeah.
standpoint of an operating system. So everything is connected here. This client process is also a process of an operating system. The server process is also a process of the operating system. What is
Okay.
special about this one, or in this case, this process has the capability to talk to the other processes that are probably running on different machines.
Okay. Right.
Yes. All right. Any other question? Okay. Now let's talk about sockets. Okay. Now the processes that we discussed, they actually send and receive messages through sockets or through something called a socket. It is not a physical entity. Okay. It's a logical entity. All right. A socket is a logical entity. Right. It's analogous to doors for different apartments in a building. Okay. So again, we have the protocol layer here for a sender, let's say, okay, and we have the protocol layer here for a receiver. And as programmers, we can actually deal with the application layer. The rest of the layers oftentimes is controlled by the operating system. So if you are an operating system designer, then you will be able to, implement protocols, all right, for these layers. But from the application layer, like I said, the application layer uses services provided by the transport layer. Okay, so from the application layer, as an application developer, you can use the services provided by the transport layer. Okay, like the TCP, you can make TCP connection or UDP connection, okay, or something else. All right, so here, let's say I have this host running an application. So there is a process for this application, okay? Now, this process will generate a message. right? And we know that that message has to go through all of this layer before it will be actually physically delivered to the next host or to the destination host. Now, to send the process from application layer to the transport layer, we use the sockets. Okay, and every socket has a number associated with it. All right. So this sender process or client process has to know the socket number, okay, of this destination process, okay, before it can actually initiate a communication. And also, as it says, 2 different sockets will be involved for message passing. All right. So whenever an application has some message, it will shove the message through the sockets to the network layer, and then the network layer will deal with the message, send it to the transport layer, and so on. Now for the rest of the layers, since they are controlled by the operating system, there is no need to have a notion of socket for the delivery of messages or packets between these layers, okay, in the protocol stack. So it's only for the application layer and transport layer. Okay, and like I said, those sockets, or in other words, for these processes to identify each other, they need some sort of identification or identifier. Okay, now we know that each host already has an identifier, right? Your device has an IP address, right? So your device is identified in a network through the IP address. Now look at this question. Can you use the IP address to identify a socket as well within a host? Or is it sufficient to use just the IP address to identify a socket for a process? Yes or no?
No, because all the processes would have the same IP address. Like they're running on the same computer.
Exactly. So that's the main reason, right? Or we cannot use just the IP address as a socket identifier for a machine, okay, for a process. Because a machine will likely to be running not just one process, not even 100 processes, thousands of processes at the same time. And what if all of those processes, they're network processes, okay? So each process will have a different socket. Now, some applications may run several processes at the same time. If you open multiple instances of the same web browser, it will be considered as if you are running 2 different applications. So they will have 2 different processes. Okay, and those 2 will have different sockets, even if it's the same application that you are running, but you are running 2 different processes or instances. Okay, so IP address is not enough. So what we do is along with the IP address, we use something else called a port number, okay, to identify a particular process within a host. Now, this port number, we often call it a socket number, but in reality, the IP address and the port number constitute a socket address. All right. Okay, for some web applications, these port numbers, they are fixed. For example, if you are using the HTTP protocol, then it is going to be port number 80. This is defined by the standards, okay? You cannot change it. You cannot run HTTP protocol on port number 81. Your operating system won't let you do that. Okay, these are designated port numbers. Similarly, for mail servers, the port number is 25. No other application can use 25, or you cannot change the port number for mail server to any other port number. Okay. All right. So I have an example here. So if you want to connect to the Queen's College Computer Science Department, all right, then you'll first have to know the IP address of the server at Queen's College, and then you'll also have to specify 80 as the port number. Okay. If you specify something else and say that I'm going to use the HTTP protocol, then your machine, host machine, will not let you send any message. Or even if you bypass somehow in your machine, the server at the Queen's College will reject. Well, first of all, it will not be listening to any other port at all. So your message will be dropped. Your message will be dropped at the transport layer. Transport layer will say that, hey, I cannot find any port that you mentioned can be used for HTTP. So it will simply drop the packets. Okay. Now, both at the sender and at the receiver, packets can be dropped at any layer. You may create a message and send it to the transport layer. Okay. Transport layer may decide to drop your packet if you do not follow the standards. From the application layer, if you say I'm using HTTP and send it to the transport layer will simply drop your message. It will not even pass it to the network layer, even within your own machine, meaning that the operating system is dropping your packet for not following the standards. So it's not just HTTP or mail server. There are fixed port numbers for DNS protocol or some other designated protocol that are used. Okay. All right. And it's needed, right? It makes sense because, well, I have billions of websites. All of them are based on HTTP. Okay. How would I know their port number if it's not fixed? So when I say facebook.com, I resolve the IP address, but I know the port number. IP address has a fixed structure, so it's easier to resolve the IP address. But think about the port numbers. If it's a 16-bit number, then even within a same machine, how many port numbers can I have? And I can assign any port number to host a website. And the clients will never know, and they will not be able to ever get service from you or access your website. So these are the reasons why these well-known protocols that are mostly used to create websites or do something else, they have a fixed port number. So knowing the IP address is sufficient, which is relatively easy to get, okay, through the DNS. Questions? Anyone? Okay. So when I say HTTP or any protocol like that, what do I mean by that? Now, those protocols, they will provide you a set of rules that you have to follow. Okay. So, for example, the HTTP, SMTP, they will tell you what types of messages that you can construct. Usually it's a request message or a response message, right? It makes sense. The clients will make requests, the servers will reply with the response message, right? And they will also have message syntax, okay? And messages will have fixed structure, and you cannot violate that. If you do that, then your request will be, it will be impossible for the server or even for the client to decode your message, okay? And we'll look at examples of structures of both request message and response message, okay? Then it also defines the message semantics, right? Like whatever that you have in request or response, what do they actually mean? Then it will have rules, right? How and when to send or respond to different requests. And these protocols, they're open source, okay? Defined by the RFC standards body, right? Request for comments body. So everyone has access to this protocol definition, right? It's not a black box. So you can build your own HTTP protocol as long as you follow all the rules provided by those standards, okay? Or follow all the message formats and etc. All right. And they have some interoperability options as well, right? Now, HTTP client can request to an SMTP server. Okay. Usually, if you are using a mail client, then your client will also use SMTP and it will talk to an SMTP mail server as well. But if you're accessing your mail directly from web browsers, then web browsers, they don't usually support SMTP. There is no need for that, okay? So you'll connect to the client using HTTP, okay? And then from there, you can contact your SMTP mail server. So there might be some interoperability, okay? As long as you follow the standards. Okay, then Zoom, Skype have their proprietary protocols. They're not open to people. So you cannot simply build a Zoom client or a Skype client. Well, people have tried that in the past. Like they would build client applications for Skype, okay? I think I used one of them as well in the past, long ago. Back in the days, Skype was the thing, not Zoom, okay? But there was something called Yahoo Messenger as well in 2000, okay, around that time. Yeah, all right. Now let's see what are the transport layer services that an application layer protocol expects. So we'll now talk a little bit about the transport layer services, okay? The application layer expects data integrity from the transport layer, right? So some applications require 100% reliability, like file transfer or web transactions, right? For example, bank transactions, right? We would like 100% reliable transfer services, right? And transport layer has a protocol for that, which is TCP, right? So HTTP, if it needs reliability, then it will have to use TCP, transport layer protocol. Now you can use HTTP and not use TCP because you have two different options. You can either use TCP or UDP. So you can build an HTTP based application which can use UDP. Okay, now the streaming applications that you see on the internet for audio or video, okay, they usually do not use TCP because TCP has some overhead. It will make sure that everything is 100% reliable, and it will also make sure that the order is perfect. Okay, when you break a file into different pieces, it will maintain the order, which may not be good for streaming. Your stream will load, slowly, or it will keep buffering. So the streaming services usually use HTTP if it's web-based or something proprietary, but at the transport layer, it's either TCP or UDP. Okay. All right. So they will use UDP. So if you are streaming and to avoid buffering or significant delay, UDP is used because UDP doesn't provide 100% guarantee or it doesn't maintain the order. So you may see some of the frames, that you are supposed to see, before some other frame. It happens sometimes. If you're watching a game, you see that, happening sometimes, right? But it's all right. We can still watch the game and, get entertained. Okay, so then, yeah, TCP, well, the application layer may expect the transport layer to provide timing guarantees. Okay, meaning that, well, transfer my message within 10 milliseconds or something like that. All right, this is what the application layer may expect. But then again, the transport layer is not, bound to provide those services. In fact, we'll see that the transport layer doesn't matter if it's TCP or UDP. It never guarantees any timing requirements for any of the application layer applications. Okay. All right. But we know that we have applications like on the internet, like internet telephony or even the online games. We need, the latency has to be very, very low. Otherwise, you will always get killed by someone else who has better connection, right? Or if I am talking to someone or as we are speaking, okay, if I say something and if you get that at night, it's of no use. Okay,
Professor,
so yeah,
I have a question. So you said that TCP and UDP, they don't guarantee what again?
guarantee what?
You said that they
Timing?
didn't guarantee something. Timing, right?
Yeah. TCP or UDP, they don't guarantee timing. They will not ever say that I'll transport your message in 20 seconds or 10 milliseconds. Now, when it goes to the network layer, it even gets worse because the network layer, it will say that I'll make my best effort to deliver your packet. Okay. All right. So that's why I keep saying this internet, it is not supposed to work, but it still works. Okay. You have probably heard this now a few times from me. All right. We still can play games, online games, right? Shooting games or something else, racing games. We can have multiple players playing together. And it seems fair, right? It still works. Okay, so there is no timing guarantee, at least on the internet. If you create a network of your own and also design the protocol stack yourself, then perhaps you can bring on something to provide timing guarantee. All right. The application layer may also expect a certain amount of throughput or data rate provided by the transport layer. Okay. Some streaming applications or multimedia applications, they require a certain minimum throughput to work. If you're watching a game or watching Netflix and it always keeps streaming and buffering, then you'll not like it. Okay. So for some applications, it requires a bare minimum bandwidth. But unfortunately, the transport layer won't, guarantee you that as well. Okay. But there are certain things that the transport layer does so that maybe it will help in some way the timing as well as the throughput. Okay. But the transport layer never guarantees the absolute timing or throughput to anyone. Okay. All right. And also there are some applications that can tolerate a little bit significant, delays or even less throughput. Let's say you're transferring a file, right? It's okay if it takes 1 or 2 minutes for me when I am downloading something. Okay. All right. As long as it's accurate, 100% accurate, I'm happy. And transport layer has that support for me. It can provide 100% reliability, but it cannot provide any timing guarantee or throughput guarantee. Okay, now the applications that can afford some delays as well as throughput losses, they're called elastic applications. Okay, and then the application layer may request security services from the transport layer. Okay, and the transport layer does not really provide any security. Now, back in the days, or in OSI model, we have the presentation layer as well as the session layer. Okay, securities could be provided through those layers. Nowadays, security is built into the application layer. So it's your responsibility as an application developer to provide security. You cannot ask other layers to provide security to you, at least when you are on the internet. But then again, if you are building your own private network, okay, having your own protocols, using your own devices that you built yourself, okay, then you can provide security at any layer you want. Nobody will complain. Okay, but when it's the internet, no, not the transport layer or the network layer will provide you security. They will provide you something else, like firewall or net operations to make things secure in general, but not to the point where your password is secured. Okay, if you do not have any security at the application layer, and if you have a logon system, if you type your password, if it goes as a plain text from the application layer, the transport layer will not even bother. The transport layer doesn't look at the content of the messages, right? It simply breaks the messages. So if you're sending password as clear text from the application layer, it will go as it is through all the other layers. Nobody will care. No, none of the other layers will care. So it's your job at the application layer to provide security. And we have tools for that, right? Previously, we used SSL a lot, secure socket layer. Okay, so the time a message goes through the socket to the transport layer, it is encrypted. Okay, nowadays we have something else, not exactly the SSL. It's called something else. Okay, we'll talk about that. All right. Okay, so here I have a list of applications and their nature in terms of data loss, throughput, and time sensitivity. So take a look at this list here and let me know if it makes sense to call or consider some of the applications can tolerate some loss and can tolerate some delays and so on.
Text messaging requires no data loss.
Which one?
Text messaging
Text messaging.
at the bottom.
Yes. You don't expect any data loss, right? You expect to see whatever that your friend wrote. So no
Okay.
data. Yeah, 100% reliability.
Mhm.
Right, it makes sense, right? For file transfer and download, we don't expect any loss. For real-time audio, video, it's loss tolerant. Okay. In certain cases, you need a bare minimum throughput or data rate for your application to work, right? Otherwise, people won't use your application. So when you build an application, you have to make it, very, very efficient, right? Then interactive games, loss tolerant. Yes, maybe. Yeah. I remember playing Counter-Strike a lot back in 2007.
Oh my God. That just took me back.
I was really good at it, to be honest. I participated in a lot of competition that was arranged in our
LAN
camp.
parties. Nice.
Yeah. So we had this LAN, right? So we had several hostels, or what are they called here? So we had 8 or 10, buildings where students could live. Boys and girls separate, but we had a big LAN. We would, team up and then play that game a lot. Yeah, at that time. Yeah. Yeah. Okay, so yeah, let's see what the transport layer actually provides. So the things that we have discussed, those are the expectations by the application layer from the transport layer. Now, what the transport layer provides actually are these, right? As either TCP protocol or UDP protocol. So TCP provides reliable transport services, right? It guarantees you that it won't, lose your packets like FedEx or UPS or USPS. Okay, it won't lose your package at all, never. It may take some time, but it will recover your packet. That it guarantees flow control. Okay, meaning that it won't overwhelm the receiver. Now, the flow control is solely between the sender and the receiver. Okay. Now, the receiver has buffers. So as the messages, keep coming to the receivers, to the receiver transport layer, it buffers messages, because clearing messages through different ports, it takes some time for the transport layer at the receiver end. So it maintains a buffer. If the buffer is full, then the transport layer will be unhappy. It keeps dropping packet at the transport layer if the buffer is full. So the TCP, it makes sure that that doesn't never happen. That doesn't happen, okay, at all. So that is called the flow control. The sender won't overwhelm the receiver. Okay, the receiver will always send back when it sends acknowledgement. Okay, it will say, hey, I have this much space left for the next message. So send a message that I can fit. Okay, so that's flow control. So it's solely between the sender and the receiver. Then TCP also provides congestion control, which is a network-wide operation. It takes into account, other devices that you have in the same network at the network core and so on. Okay, so it will throttle the sender when it sees that the network is overloaded. And how to know that? Well, if the TCP sees that a lot of packets are getting dropped, so it's an indication that perhaps some of the routers along the path is not doing its work properly, or it doesn't have a buffer space, in it, etc., etc. Then TCP provides connection oriented. Okay, so before you can use TCP, there needs to be a call, a setup. Okay, so that resources can be allocated. Now it is similar to circuit switching, but the overall process is packet switching. Okay, so it's a little bit complicated that we discussed in the other day, and we'll talk about all of these things. Chapter 2 involves detailed discussions of all of these points. Okay, this is just a summary. Okay, so TCP is connection oriented, meaning that even before the data transfer happens, all the resources are reserved both at the sender and at the receiver. And TCP does not provide any timing guarantee or minimum throughput guarantee or security. Okay. Now, if you look at the UDP, it is an unreliable data transfer protocol between a sender and receiver. So it doesn't provide reliability. It doesn't provide flow control. It doesn't provide congestion control. It is not connection oriented. Okay. And forget about timing or throughput. All right. So having UDP is like having no transport layer protocol. All right. But we still need UDP for some reason. Okay. All right. But from the standpoint of the services, it is as if it's not providing any services. It's just sitting there. Okay. But it does some services that we'll see in the next chapter. Okay, not today. All right. But if you think from the standpoint of reliability, flow control, or even fair share of the network usage, UDP will always keep sending messages. Let's say you have a video that you are streaming, okay? And you'll be using UDP, right? You'll not be using TCP because in that case, it will be very slow for you, okay? It will not be real time, all right? So whatever that you give to UDP, it will simply forward it to the network layer and it will go to the network. Now, if you have, let's say 10 users and 8 of them are using UDP, meaning that always keep sending whatever they have in the network, then if one of the users is using TCP to get reliability, then that user's definitely the throughput and timing will be a little bit off. Okay. So oftentimes people say, is it even fair to have UDP as a protocol at the transport layer? Okay. And that is a big question in the research community. Okay. But we still need UDP. Okay. That we'll see in the next lecture. All right. Questions? None. Okay. All right. So now here I have a list of applications. Okay, their application layer protocol and their corresponding transport layer protocol. Okay, so look at this list and see if it makes sense. And we can also take a break. So I'll leave this slide on the screen. Okay, and I'll be back around 1:30. Okay, like 12 to 15 minutes from now. Sounds good. All right, I'll see
Sounds
you.
good.
Okay, so any question from this slide? Okay, so now let's see how the transport layer protocols are actually protected from the application layer. Okay. So the typical TCP and UDP sockets, okay, they're not encrypted. So as I said before, if you send a clear text password from the application layer, then it will go as it is. Okay, but there are other, libraries using which you can provide security to the transport layer from the application layer. We have SSL or TLS, transport layer security, right? Which can provide encrypted TCP connections, okay, or keep the data integrity, provide end-to-end authentication. Right. So now these libraries, we can consider them as part of the transport layer, okay, but they're used by the application layer. Okay. So yeah, we'll have discussion on these libraries, okay, in chapter 8, which is solely focused on the security of data communication. Okay, so now let's look at peer-to-peer applications, okay, and analyze them. So again, what is a peer-to-peer architecture? Okay, we saw this slide in the first half of the lecture, right? So we have N systems, they talk to each other directly over the network, and there is no notion of servers, actual servers that are always running or have a fixed static IP addresses, etc. Okay, in P2P, the peers, they come and go, they provide services, they get services, all right, and they don't have fixed IP addresses. Well, if they have fixed IP addresses, that's fine. Okay, that's probably beneficial, but it's not a requirement for a peer-to-peer architecture. And we look at the BitTorrent protocol, okay, but there are other protocols like VoIP, I mean CAN or VoIP protocols, okay, that use this architecture. All right, so let's start with an example, okay, to show the performance of server client architecture and peer-to-peer network architecture. All right, so let's consider this setup where we have a server, okay, and it has a file of size F, and all the clients here, okay, the server needs to send this file of size F bits to all the clients. And the server has an upload capacity of US, the upload capacity of the server, and different clients, they have different upload and download capacities. All right, so if we consider this arbitrary client, then it has UI upload speed and DI download speed. Now for server client architecture, all of these clients, they will get the file directly from the server, because that's the essence of the server client architecture, right? In server client architecture, the clients, okay, they cannot talk to each other directly, or they cannot get the files from each other. Okay, so here we are somewhat misusing the terms a little bit. Even in server client architecture, we are calling the clients peer. Okay, so don't get confused. All right, and also consider that we have this network which has abundant bandwidth, or in other words, this network is not a bottleneck for us. For now, we can assume that, just to analyze the efficiency of server client architecture and peer-to-peer architecture. Okay. All right. Any question? So the bottlenecks are basically these links: the upload link of a server, the download link of a client, the upload speed of a client. Okay. These are the bottleneck links, not the network core. Not the network core. All right. So now how much time does it take for the server to distribute, this file to all the clients if it's a server client architecture? First of all, any question about this setup here? Anyone?
So when you say the bottleneck of the upstream and the downstream, that's like from last lecture,
Yes.
the amount of time it takes to transmit data. Okay.
So these are basically the link capacity of these links. Okay. There may be a edge router here. There may be an access link here, or some routers connected in the network. We're considering that they have abundant bandwidth, or the link capacities of the devices that we have in this part of the network. It's sufficient. It's not going to be a bottleneck for us. Okay. A client will take long time to download the file from the server if it has a low capacity download link. Or in general, all the clients will suffer if the server has a low capacity upload link. Okay, this is what we are saying. Okay, any other question?
So you're saying that the bottleneck would be like on the local level instead of like in the like on the network?
Yes.
Okay.
All right, so we'll now try to come up with this term here. How long does it take for all the clients to download the files or get the files? Okay, now when I say that in server client, it involves that the server needs to upload the file into the network before the clients can download, right? Or we can also assume that as the server is uploading, the clients are also downloading. Okay. It's not like the server has to first upload the whole file into the network and then the clients will be able to download them. Both the uploading and downloading can happen in parallel, just to make things simpler, the setup simpler, so that we can actually analyze the performance of the server client architecture and peer-to-peer architecture. All right, so now first let's focus on the client server architecture. Okay. Now, can you estimate the time it will take for all the clients to, or the maximum time it will take for the clients to download the file if it's a server client architecture? So you'll have to look at different components of this transfer. You'll look at how long does it take for the server to upload the file. Now, it doesn't matter how fast a client can download. If a client can download the file in, let's say, 5 seconds, but if the server takes 10 seconds to upload the whole file, then ultimately that client will not be able to download the file before 10 seconds, right? So we'll have to take into account all of those things to come up with the final answer. right? So yeah, so before we look at the final answer, okay, let's break it down. So for server client, we know that the server has to sequentially send n different copies of the file to all the clients. In server client, for this client to get the file, the server has to upload the file to this client. For this client, again, the server has to upload the file. Okay, it's like, let's say two of you are trying to access a website. The server has to give you the same files to both of you separately. Okay, this is how server client works. So this is how actually we access the websites on the internet, right? Okay, so for n clients, it's correct to say that the server has to upload n different copies of the file. Okay. Now, how long does it take to upload just one file for the server? The upload speed of the server is US and the size of the file is F. So it's basically the transmission time that we are talking about, the upload time, right? So it's F over US. And since we are asking about the total time for all of these clients to get the file, copy of the file, so it will take this much time for the server to upload n copies of the file, n times, right, the time it takes to upload one file. Is this clear?
Yes.
Yeah.
Okay. So that's from the standpoint of the server. Now let's think about the clients. Okay. Now each client should download the file copy, right? And let's say I have a client that has the minimum download rate. The link capacity of one of these clients, you know, is minimum. So for that client, we'll take it longer compared to all the other clients in the network to download the file. Okay. So the client with the minimum download rate, if we call it dmin, okay, then for that client, it will take F over dmin time to download the file. Okay, and different clients will have different download times. That's for sure. We are, for the sake of this question, we can consider only that client that will take the longer time. Okay. If one client takes 2 seconds, another client takes 4 seconds, and then I ask you, what's the maximum time for all the nodes or clients to get the file, then we'll definitely consider the client that takes the maximum amount of time. And the client that has the lowest link capacity will take the maximum amount of time to download the file. Okay. All right. So to answer this question, how much time to distribute, you know, this file of size F from the server to the client, is this. The maximum of the component that we found from the server's perspective and the maximum, you know, that we found from the client's perspective. Okay, so it's the max of this term, the time it takes for the server to upload all the n copies of the file, and the time it takes for the client that has the lowest link capacity. Is this clear? So if the server takes 10 seconds to upload n copies of the file, but if there is a client in the network that takes 15 seconds to download its copy, then we'll say, well, it will take 15 seconds for the server or for the whole network to download the file, right? Questions? None? Or is this clear to everyone?
Yeah, more or less. Yeah.
Okay, now let's think about the client or peer-to-peer architecture where a client can download the file from another peer as well, okay, including the server. Now in peer-to-peer network, the server itself is also a peer, right? So we'll count the server as well in our calculation, okay? Now, what's the idea of peer-to-peer network again? If a peer or a client, I'm misusing the terms a little bit here, okay? So don't get confused. So if a peer or the client needs a file, it can get the file from anyone, from a single peer or from a list of peers or from all the peers that we have in the network, right? So if we consider that, then we can say that, well, now in this case, the server peer, okay, before you do that, just look at this expression one more time for server client. As you can see, as the number of clients increases in the network, this term will increase, okay? So that's one point. Okay, now let's go back to our discussion on peer-to-peer, right? So now, since this is peer-to-peer network, and we are considering the server as a peer as well, so we can say that, well, the server now needs to upload just one copy of the file in the network, okay? Just one copy of the file in the network would be sufficient since this is a peer-to-peer network, okay? All right, now, how long does it take for the server to upload just one copy? It's simply 1 over US, where US the upload capacity of the server. And again, we have this condition, all the clients must download, a copy of the file. And again, we can also consider the client that takes the maximum amount of time to download one copy that has the least download capacity, okay? So if dmin is the client with the least download capacity, then that client will take F over dmin. And then comes the power of the peer-to-peer network, okay? Now a client also has this chance, right? Or overall, now we can consider this. We can consider the whole network and sum up all the upload rates, of all the peers that we have in the network, okay? That will be the total upload rate of the network. And also we have this condition that all the peers in the network must get a copy of the file. So what we can say that now the total upload rate of the network is this, right? Summation of all the upload rates of the file clients, since each client can now, or all the clients can now upload the file on the network to help, all the other clients, okay? So there's the total upload rate, and at this upload rate, we have to upload n copies of the file, since again, n different clients will have to download the file, right? Or in other words, the whole network has to help n different clients, right? So it's not just one file, copy of the file, okay? Or not just F bits, it's n F bits, okay? So now if we take into account the total time, now we can say the total time will be at least the maximum of the time it takes for the server to upload one copy, or the time it takes for the, slowest peer or client in the network, and also this term, NF over the total network upload capacity. Questions? Is this clear to everyone? All the three terms that we have considered here? Go ahead.
So can you just explain why it's NF over the US and the summation of all of the uploads, like at the end of the equation?
Okay, so it has two aspects to it. First of all, it's about the question. So it's asking how long does it take for all the clients to download the file? Okay. Now, if you think about that, then in total, how many bits are being downloaded in the network actually? The file has F bits and all the end clients are downloading F bits. Okay. So that's NF bits. So that is one of the requirements. We need to make sure the whole network, well, excluding the server, if server was included here, then we would write n+1 times F. Since server already has the file, we can say that, well, the server doesn't need to download the file, right? Okay, so it's about the client. So this many bits, have to be downloaded in the network by n different clients, okay, or peers. We're thinking from the overall network perspective. So this many bits needs to be downloaded, and this many bits will be made available by all the peers in the network, okay? Meaning that we can now consider all the upload link capacities of all the peers, okay, including the server. And that's this, the upload capacity of the server plus summation of all the upload capacities of all the n peers, I equals to 1 to n, okay? So we know the total amount of bits to be downloaded in the network. And we also know the total, upload capacity. All right. So loosely we can say that, okay, this is the time it's going to take for the whole network to download the file. Okay, well, you may think that, well, we should probably incorporate the download speed of all the clients as well. Well, if you're thinking about that, then yes, you are also right. Okay, we can have probably another term as well. Okay, instead of having just 3, we can incorporate another, but it suffices to include only this one. Okay, in this case for us, we can assume that usually if you look at any connection, the download speed is always higher than the upload speed. Okay, but if we want it to be completely accurate here, we would probably include another term here where it would be NF over summation of UI only. Okay, since in that case, we'll have to exclude the download rate of the server, right? Here, simply there is no notion of the server peer to download the file. Okay. So let's try to do that. Okay. Just for the sake of completeness. So I'll just add another term. And it's gonna be this. Now it's gonna be this. And move it maybe a little bit on the left.
Professor,
Just one sec. Yeah, go ahead.
do you gotta memorize the formula for the exam, or?
Do you think that you need to memorize the formula? As long as you know what is going on, can you come up with the formulas yourself?
Nah.
Who can come up with the formula without knowing the formula? No one? Come on, guys. Which part is confusing? It's just calculating the transmission time for different cases and nothing else. So it's gonna be number of bits over the capacity for all the terms. You just have to consider all possible scenarios. Okay. Yes. So it is supposed to come here. Greater than or equal. Right, looks good now. Do you have any questions about this? So yeah, the analysis of peer-to-peer network, it can be a little bit tricky, but it's doable. As long as all the information are given, also the scenario is explained, okay, you should be able to come up with the equation. Is this term clear, the first one? Who can tell me what is this telling us, F over US, in this peer-to-peer context?
It's the time to send one copy, like one copy of data from one server to the other.
Okay. It's the time it takes for the server to upload the whole file in the network, right? So if it takes, let's say, 30 seconds for the server to upload the whole file, then all the other peers combined, having their capacities combined, they cannot download the file less than 30 seconds, right? So that's why we have this term, maximum of these terms. So if this is dominating, then there's the time it will take at least for the network to download the file. If there is one client which is very, very slow, it may be the case that it takes 2 seconds for the server to upload the file, and collectively n-1 nodes download the whole file also in 10 seconds. But there is one peer or client that takes 20 seconds because it has very, very low capacity. In that case, this term will be dominating, right? So we have to say that, well, it will take 20 seconds for the server to distribute, the required information to the whole network. All right. All right, so think about this, okay? And let me know if you have questions in the next lecture. Now, if you look at this expression, then you see that we have a term n. So as the number of clients or peers increases in the network, the amount of bits that needs to be downloaded will also increase. So does the total network capacity. So if both of them increase, overall, they're getting divided each other. So the ratio is going to stay almost the similar. Okay, and this also applies to this term as well. Okay, so here I have this figure here. On the x-axis, we have the number of clients. On the y-axis, it's talking about the minimum time it takes to distribute the file in the network. And we are considering this, okay, where the server upload rate is, the client upload rate is U, okay? And all the clients have the same upload rate U. And the server is 10 times faster than all the clients or any of the clients in the network. And the slowest client, okay, is greater than the server upload time. The slowest client in terms of downloading the file. And what else? F over U is 1 hour. Okay, so I'm using these numbers. If we keep increasing the number of clients in the network, then this curve is showing the time it will take for the server client architecture. So as you can see, as the N increases, the time increases linearly. Okay, so if we have many clients, then it will take more time. Okay, linearly more time for the server to upload the file. But for the peer-to-peer architecture, okay, it increases a little bit, right? Fractionally, but not as much as the server client architecture. So this figure is telling us the peer-to-peer architecture is definitely better for file distribution in the network. And it is also better for a lot of things, other things. All right. Questions? None? Anyone? Anything? Before we discuss the BitTorrent protocol? So one of the groups, has to implement the BitTorrent protocol as the project. Or maybe multiple groups will do that. We have 8 groups, right? And I have 3 or 4 projects in mind. So at least 2 groups will implement the BitTorrent protocol, which is a peer-to-peer network architecture, uses peer-to-peer network architecture.
Professor, are you assigning the projects or are we choosing them?
I am assigning the projects. So I'll toss a coin and then I'll probably toss 2 coins. Okay. If I have 4 projects, then 2 coins. If you get head, then you'll get 1 project. If you get head tail, then you'll get another project. Well, in case all the groups get head, then I have to make it complicated. Okay. Yeah. Any question about the server client architecture? Anyone? Or the example that we have seen? And okay, all right. Now let's talk about the BitTorrent protocol. Okay, it's a peer-to-peer file distribution protocol. It's an application layer protocol. Okay, where a file is divided into chunks of this size. 256 kilobyte, not kilobyte, kilobit chunks. The size of a chunk. So in the application layer, let's say you have a file of size 1 megabyte. Okay, then it will be divided into 256 kilobit chunks. Okay, at the network layer, in the application layer, not in the transport layer. If it's needed, then it will even be divided into transport layer, but you don't have to worry about that. The operating system will take care of that. But for this BitTorrent protocol, okay, at the application layer, the message is divided into, or file is divided into chunks of this size. And this is a peer-to-peer network. So peers in this network, okay, torrent, send or receive file chunks. All right. Now chunks can be received out of order. So at the destination, they have to be ordered before they are merged, right? It makes sense. So you can get the first chunk and the last chunk, and then probably a few chunks from the middle. When will the download complete? When you have all the chunks, okay? Then you will do the combined process. Okay, so this is the overall network. There will be multiple peers, collectively called torrent, right? Group of peers exchanging chunks of a file. Okay. So, and this connection will change. It will not remain static. For some time, this client will be connected to, let's say, these 3 different other clients or peers. After 30 seconds, this connection will change. It will connect to probably this one, depending on some criteria that we'll discuss in a moment. Now, in this BitTorrent network, there is a component called a tracker, okay, which kind of behaves like a server, but it is not a server from the context of our discussion. If it was a server, then it would also participate in the file distribution operation. But this tracker server does not participate in the actual file distribution, okay? So this is a peer-to-peer network, but it's also has a tracker server, and it's needed, right? It keeps tracks of all the IP addresses of all the peers that are active in the network or that are participating. They can be inactive, but overall they're participating in the network. Okay, and if you have used any torrent client, okay, or application, then you know that you first have to download a torrent file, right? .torrent or something else. So basically you access a tracker server, and from that tracker server, you download a file, torrent file for a particular, resource that you are trying to access. Maybe it's a software or a movie or something else. Okay. So for that particular file, the torrent server or the tracker will have a torrent file inside which it will have the list of all the participating clients or peers in the network. Okay. And it gets updated over time. All right. And this is what you do. You enter a torrent site and download something whose size is, let's say, 1 or 2 kilobyte. Then you double click on it, then the actual operation starts. So inside that file, if you open it, you will see a list of IP addresses. Or it will tell you, which hosts in the internet is participating in this particular distribution of this file, okay, or in the distribution of this particular file that you are trying to download. Okay. Okay, so let's consider Alice. She arrives and wants to download this file. So first of all, she will talk to the tracker server and obtain the list of participants that are currently in the network. Okay, this torrent network. Okay, so once she has the IP addresses of all the participants, then she will randomly choose a few of them and contact them to give her chunks, different chunks. Okay. So overall, simply the architecture works like this. Now, Alice has options to which, clients she should connect to for requesting files. And also, while requesting files or receiving file chunks, she will also have to upload chunks to the network. If she doesn't, then the other peers will not send any chunk to Alice. Okay. So that's how BitTorrent, confirms that whoever is downloading some chunks is also uploading some chunks. Questions?
Is there anything, because I remember like back in the day when like 10 years ago when I was in middle school and I would like download music off of the internet, a lot of it was BitTorrent. BitTorrent in my brain automatically is like illegal. Like torrent sounds in my brain like something's wrong, something's against the law. Is there nothing wrong at all? Because what it seems like from what you're teaching us is there's nothing wrong at all with torrents.
Yeah, like I said before, this protocol is a very useful protocol. It's us as users who are misusing it. Now, if you are distributing a file, copyright file using BitTorrent, whose fault it is? Is it your fault or the people who are developed BitTorrent?
Well, I'm the one well, if I'm using it and I'm using it properly, then it's not my fault, it's the people that's downloading it.
No, let's say you have a copy of a music. You bought a CD,
Right.
copied the songs on your computer, then you created a torrent for it.
Right.
Now, what you are doing here is you are distributing the songs that you are not supposed to do.
Oh,
through
then
torrent.
that's my fault then. Then the one distributing it is wrong.
Well, you could use a flash drive to give the songs to your friend. Is it the fault of the pen drive? No, it is not.
No, right.
You are distributing, copyright materials without the consent of the actual owner of the material.
Right.
Just because you
Okay.
bought something doesn't mean that you bought the copyright. Anyway, so you get the idea, right? So yeah,
Absolutely.
it is used heavily to, distribute movies, and torrent servers all of them are usually outside of the US. Usually in the US, if you run a torrent server, then people will show up at your door, okay, at some point.
Really?
They'll send
Professor,
you a letter. They'll send you a letter just for downloading too much, downloading too many movies.
If you're using BitTorrent, this is the thing, right? You can just download. If you're downloading, it is ensuring, this protocol is ensuring that you are uploading as well. So it's a problem when you upload. You can watch or stream movies as you want from websites. There are many websites that host some of the contents that are copyright, but you can get them for free.
Wow.
As long as you are watching them, streaming them, downloading them, it's not an issue. It's on them who are hosting them. But if you are using BitTorrent, then this protocol ensures that for the sake of fairness, okay, you will also upload. You may not know this, you are uploading. If you are using BitTorrent protocol, then you are downloading as well as uploading, okay? Because if you do not upload, at some point, no other peer in the network will send you any chunk. It's about
Oh,
mutual trust.
I see.
It's about mutual trust. If you get chunks from 3 different peers, okay, then you'll also have to send chunks to them. Let's say they have chunks from chunks 1, 4, 5. So you can get those chunks from them. And if you have chunks 8, 9, 10, you will have to send those chunks to those people, or to those people who do not have those chunks.
Yeah, it's like a big pool.
Yes. Okay. And I have heard stories of FBI showing up at your doorstep.
Really?
Yep.
Huh.
Back in the 90s, the band Metallica sued their fans for distributing their music. They sued a kid.
Yeah.
They seeded too much.
Wow.
All right. But as computer science students, right, we need to know of these protocols. We can use this protocol locally, okay? We can create a network, and then we can use this protocol to distribute files. Or if I am the owner of something, I can definitely distribute that using BitTorrent without an issue. Nobody is gonna show up at my doors, right? If I have the ownership of the file that I'm distributing, doesn't matter if I'm distributing through BitTorrent or through flash drive or simply by uploading on Google Drive. People also do that, right? They upload movies on Google Drive and then give the links to other people, right? So BitTorrent is a transparent protocol. That's why it's risky to use BitTorrent to distribute content that doesn't belong to you, okay? But if I have something that belongs to me, I have the ownership, I created this, then I can use whatever I want to distribute as long as it is legal stuff, right? From the standpoint of so many things. Okay, so now a little bit more about Alice. So when she joins the network, so she gets the torrent file from the tracker server, and inside it, she has the list of all the participating clients. So from there, she will choose 3 or 4 of them. And initially, she will not have any chunks, but over time, she will accumulate chunks, right, from other peers. Okay, she will also register with the tracker server, right? So that others know that she's also part of the network, okay? If someone else later comes to the network to join the torrent, then they will know. Okay, but the existing peers, they will already know. Since Alice will request to them for chunks, they will know there is a new peer, okay, in the network. So while downloading chunks, peer also uploads chunks to other peers, okay? So it's like a mutual, understanding between the peers, okay? Now you may be downloading chunks for a set of peers, and you may be uploading chunks to another set of peers, but they will always overlap, okay? This process just allows you to, change the group of people that you are, exchanging with. But again, since this is a peer network, you can come and go anytime you want. If your machine is on and running the torrent, then you'll be participating. If your machine is off, then you'll be offline. You cannot download from anyone. No one can either download from you, okay? Or you can be selfish as well. Once you have the whole copy of the file, you can simply leave the torrent, right? That's being selfish. But you are supposed to be there and help others who are right now trying to download, even if you have the whole file. But what we do, as long as our file is downloaded, we delete that, delete the torrent, right? Okay, so now while requesting chunks, let's say at any given time, as you can assume or see that different peers will have different chunks, right? So periodically, Alice, she'll ask each peer for a list of chunks they have. If Alice is connected to just a few fixed set of peers, then what if those peers collectively do not have the whole file? Then it will not be possible for Alice to download the whole file. So over time, she will have to update the list of peers she interact with, okay? So that's why she'll be asking over time. From time to time, she'll be asking to her peers, asking, what chunks do you have to offer me, okay? So from that, she will figure out the chunks that she is missing and that are also in her, neighbors, okay? And it makes sense to request for those chunks that are the rarest. If she's talking to 4 different peers, and let's say all of them have almost all the chunks, but one of the peers only have chunk number 30, and none of the others have it. So she will first request the chunk number 30 because this is the rarest, right? Okay, and it makes sense to look for those chunks first. So this is what happens in BitTorrent, or this is the overall process for requesting chunks, okay? Now, while sending chunks to others, Alice, she will use this protocol, okay? Tit for tat, okay? So typically in BitTorrent, a peer is connected to other 4 peers, okay, for exchanging chunks. So Alice will be, getting chunks for 4 different peers. She will also be sending chunks to those 4 different peers, okay? And Alice will not be sending to the rest of the peers apart from those 4, okay? So it's like she's choking the rest of the peers in the network, okay? And also in every 10 seconds, where is my cursor? Okay, fine. have an old computer, so my computer started making noises. Okay, so every, let's say 10 seconds, she will re-evaluate those 4 neighbors that she is, working with. If she finds that some of them are not sending her chunks, then she will not send them chunks as well. Okay, and any question?
Professor, what's in the chunks? Like, what is the chunks that Alice is giving to the peers?
So it's the file, right? I said a file is divided into different chunks.
Yeah.
Is it confusing?
So let's
It's like basically like you're contributing, like if you're trying to download a movie, like let's say you go to download like a movie or whatever from a torrent site, you are downloading pieces of that movie that other people have contributed to it. Like basically you're not getting the file like directly from anyone in particular. You're just like collecting little pieces or chunks of that file or files from the network.
Yeah, from different peers. Yes. All right, so every 30 seconds, she will randomly select another peer in the network. Okay, so she already has 4 peers to work with. Every 30 seconds, she will select another peer in the network randomly and unchoke that peer. Okay, she will send some chunks to that peer. It's called optimistically unchoking. Okay, so she's hoping that now if I choose someone else in the network and send them some chunks, perhaps I'll get some chunks from them as well in return. Okay, that will, fill in the missing chunks at my end. Okay, now if she's satisfied with the performance or with the chunks with that the newly discovered or chosen peer, okay, if she's satisfied, then she may change the group she interacts with. Okay, she may kick out one of the existing members from her group of 4 peers and add the new peer to that group. Okay, it all depends on whoever contributes more to the network. Now, typically the people who have higher upload speed, they will get better peers for downloading chunks. So if you have higher upload speed, that means you can upload more chunks to other people. And in BitTorrent, when you upload more and more chunks to the network or to different groups of 4 peers, it's likely that you will also get all the chunks easily. All right, so with better upload speed, you will always be performing better in the BitTorrent, or you will be able to download your file in less amount of time compared to who has, let's say, least upload speed. Okay, so let's consider this Alice and Bob. Alice, she's right now working with these 4 peers in the network, and we have Bob right now, he is working with these 4 peers. Okay, now Alice, she has choked all of these peers here, right? But we know that optimistically she will unchoke at some point, let's say Bob, in the next 30 seconds, and she will send some chunks to Bob. And if Bob reciprocates with some chunks that Alice really needs, then she may get rid of one of her existing pairs, okay, and add Bob to the list. Okay, so in this case, if she is happy, then she will remove, she basically here is removing this pair and adding Bob to her list of top 4 providers. Okay, so as I said, higher the upload rate you have, it's likely that you're gonna download the file easily, or the people who have higher upload rates in BitTorrent network, essentially they will group together over time. Okay, and get the file faster. All right, so this is overall the BitTorrent protocol. Okay, any question? Now, this is an application layer protocol, and you know exactly how it works. Now, for your project, you'll also have to use transport layer services. So when, let's say, Alice makes a request to Bob, she'll probably use TCP as a transport layer protocol, right? So you'll have to implement this whole protocol, application layer protocol, but you can use whatever transport layer services that are available for you, okay? And it's gonna be a TCP, right? Because you wanna ensure that it's 100% reliable. If you are receiving a chunk, that chunk is correctly being received, right? You have to make sure of that. It's not that complicated, is it? It's not. Okay. And in a group of 5 people, yeah, you can create, one of them can act as a tracker server as well as one of the peers, since only we have 5 people. And instead of keeping, top 4 providers, you can keep 2 top providers. Okay, so you can play with the numbers so that all the 5 group members can contribute and also see actually how the protocol works. And yeah, in the past semesters, few groups have actually implemented this protocol really well, right? Some of them have implemented the email protocols really well. I mean, really well. So you will have server processes, client processes. Alice will sometimes act as server, or she will have server process. She will also have client process. You can incorporate or write everything in a single file, or you can make it modular as you wish. Okay. But you'll have to make sure that once you run the program, okay, everything is taken care of. It's not like you'll need 2 different clicks to, work Alice as a server or a client. Everything has to be automated. Questions about BitTorrent? Anyone?
Since that it's delivering chunks of data from the peers and it's from like different sources, it seems, wouldn't that mean that some of the data might not be like consistent with other chunks of data? Like one chunk of data might be of lesser quality than another chunk. So if I was downloading a movie, wouldn't part of the movie, could it be with BitTorrent that part of the movie is in a lower definition than the other part of the movie?
So it will start from one peer, right? So one of you will have the whole file initially, let's say. Okay, or you can also start like this. You can have a file and divide it into multiple pieces, and you will have some of the pieces in one of the pairs, some of the other pieces in distributed to the other pairs. You can start like that as well. So as long as you have this, all the pairs will have the chunks of same quality, right? So initially information will spread slower, or this is the case for BitTorrent. Let's say if I create a torrent initially, it's only me who is contributing, right? If someone else later joins, then it's just 2 of us. But over time, more and more peer will come, okay, and more peer will have many different chunks, okay. All right. So you have to adjust. Since we only have a few people, you can have an initial file divided into, let's say, 100 chunks, and each people will have 20 chunks, different 20 chunks, okay, each people. So that's in total 100. Then you will start the BitTorrent protocol. Okay. Now
Okay.
you can get rid of the tracker server. Since it's only 5 people, you can assume that IP addresses of each other's, and that will be the case, right? You will know the IP address of your machine. You can just let your friend or group member know that, hey, this is my IP address. So whenever you want to request a chunk, use this IP address. Okay. All right. And you'll also have to use a port number, usually the operating system will take care of that for you. But if you're creating a server, you can choose your own port number as well, okay, from the application layer. That's usually in the order of thousands, like 5,000, port number 5,000. You cannot use 80 or 25 or the port number for the DNS that are reserved port numbers. Okay. All right. So as long as you have the basic protocol implemented, it's all right. You can get rid of the tracker server. The job of the tracker server is to distribute the IP addresses of all the clients, right? Since it's only 5 people, you can just share your IP addresses with each other. And you may run into some issues, engineering problems. So you'll have to figure those out, how to solve them. Now, if you're using your home Wi-Fi, then you'll get an IP address from your router. Now, if you give that IP address to your friend, it's unlikely that your friend will be able to find you on the internet because of the NAT feature that we have, network address translation. All right. Later, we'll talk about the notion of private IP address, public IP address, or real IP addresses. Okay. So as long as you are connected to the same network, all of you, then you can use the IP addresses without any issue. Let's say you can create a hotspot using a phone and then connect all the computers to that phone just to build the network. Then on top of that, you can run the peer-to-peer protocol so that you do not have to worry about connection initially. If you use the Queen's College Wi-Fi, then Queen's College Wi-Fi won't let you, create a hotspot. But you can still use the IP addresses that you get, okay, from the Queen's College Wi-Fi. So, or you can use some web servers if you have one already, okay? So all of you can connect to that web server like Amazon AWS, okay? All right. All of you can connect and then you will be assigned a fixed IP address from there, okay? And then use those IP addresses to connect to each other. So it's up to you, okay, to fix the connection problems. All right. I won't be able to help you with that. So it's basically an engineering challenge for you, okay? So in the past, the easiest way people did it, all of them connected to a mobile phone, basically. You do not even need an internet connection for that. If you can create a hotspot from your mobile phone and all of your friend connects to the same mobile phone, then they will be assigned, certain IP addresses, which will be managed by your phone and not by the internet. All right. So first thing that you have to do, you have to create a network where everyone can talk to each other. And how can you be sure that everyone is being able to talk to each other? You can write a basic application saying like hi, hello type of communication between two devices just to check if the connection is all right or not. Okay. So once that is all right, then you can implement the BitTorrent protocol on top of that. Okay, so here I have examples of sockets, right? We know what is a socket, right? So we'll look at a few examples, bare minimum examples, since this is not a programming class, okay? And these examples will show you how to use a TCP socket or a UDP socket, okay? Or how to specify if you wanna use the TCP for transport layer or UDP for transport layer. And in this example, we are considering this application. So a client reads a line. So it's basically a messaging application, okay? A client reads a line from keyboard and sends that to server. We are using client-server architecture, okay, for the example. Then the server receives the data or line and converts that to uppercase characters, all uppercase characters, and sends it back to the client. okay, and then the client displays it on the screen. So this is the simple application, right? Now, you know how UDP works, okay? So there is no handshaking, there is no connection setup, okay? And for UDP connection, you have to explicitly, both for TCP and UDP, for initially you have to explicitly set the IP address of the server. From the client, you'll have to say, I'm trying to reach this IP address at this port, okay? You'll have to specify that. And if it's UDP, then it's unreliable, right? Your messages can be lost, and it will not be retransmitted by the transport layer. Okay. So here we have the overall flow. So first of all, the server has to be up and running. So the server has to create a socket that can accept connection, okay? And in Python, you can do that using this line of code, okay? I know you know, I think all of you know Python. If you don't, it's a very easy programming language. It will take you less than a day to learn Python. You just need to learn the syntaxes and those stuff, right? Then you know how to program anywhere. So here the server is being created. Then once it is up and running, okay, then you'll also have to create a client socket at the client, okay? Now there are certain parameters that you'll have to use in Python to indicate if you are creating a TCP port or an UDP port, client port, okay? So given that you know the IP address of the server, then you will basically connect to that server and send the line, and the server will get the line and then reply back after making all uppercase. And then from the client, you will basically display that. So this is the overall workflow, but I have the code for the client for this case, the UDP client, okay? So go ahead and take a look at this after the class. And I also have the code for server client, server, UDP server. So if you write this piece of code, okay, and this piece of code, they should be able to talk to each other over the internet, as long as you provide the host name, correct host name of the server. Host name is the IP address. You'll basically specify the IP address, okay? And also you open a server at port number 1200 at the server side. So from the client side, you'll have to specify 1200 as well, okay? And there are a lot of things that are done for you automatically by the operating system, because when the server connects or sends back data to the client, it has to also know the IP address of the client and also port number of the client, right? So the operating system takes care of that for you, okay? So yeah, take a look at that as well. So whenever you use the send to function from the client, the operating system automatically includes your IP address as well as port number, okay? So that the server can reply back, right? But that is not shown here, okay? It basically is saying to you, okay, I'm trying to connect to this server and this port of the server, okay? So this is the server side, this is the client side, this is the server side, and the previous one was client side for UDP. You can do the same for TCP as well, okay? TCP is connection oriented. So before even you start transferring data, you'll have to make a connection, okay? So this is the overall workflow. Again, after the class, take a look at this. And I also have the code for TCP client and TCP server. So what you have to do is replace this server name with the actual IP address. If you use the local host, you know what is the local host, right? You can have both the server and the client in the same machine. So I would probably start there. Instead of first trying to connect to another machine over the internet, I'll use these pieces of codes and I'll run the same, both server and client on my machine, and use the local host as the server name. And I'll try to see if these two processes can actually talk to each other. Okay. So two different terminals, run the server code, run the client code, specify the local host as the server IP address and then type some message from the server client, see if it is displayed on the server side. Let's look at the code. So whatever that you type will not be shown at the server side, but the server will actually get it and make everything to uppercase and then send it back to you. So from the client, as soon as you type something on lowercase, you should also see another line, okay? The same line, but all uppercase, okay? That way you will be able to, you'll be sure that actually that line was sent by the server. So I'm not going to explain the code here. It will not make any sense, okay? If you look at the code, it will make perfect sense for you, okay? So again, after the class, please try that, all of you, independently, even before you talk to your group members. And the projects will be assigned after we complete all the protocols, okay? Probably tomorrow or the day after tomorrow, all right? And we have 5 more minutes or 8 more minutes. So let's stop it here for today. In the next class, we'll talk about web and HTTP, the email protocol, as well as the DNS. All right. Questions, if you have any.
So even if we're implementing something like BitTorrent, first we would have to connect the computers with the socket programming.
Yes, that would be the way to approach the project. Okay. So even before you actually implement BitTorrent, make sure that all of you 5 people can actually talk to each other over the internet through socket programming. So you'll create a skeleton. Well, you'll have to choose the architecture first. And BitTorrent, it's a peer-to-peer architecture. So you cannot use the server client architecture for BitTorrent. So it will be a peer-to-peer architecture. Then you will create a server process, client process using these pieces of code, or you can use any other library as well. It doesn't have to be Python. It can be PHP or JavaScript or simply Java or something else. And every programming language has socket, support for socket programming, more or less.
Okay.
All right.
So
So-
then the computer would be the server and the client through the socket programming in that case.
What happened?
All right. So yeah, first try it on your local machine, run both the server and client on the same machine and see if this happens. If you type something, then you get back the uppercase of the line in the uppercase letter side. So once that works, then talk to your group members, okay? And then one of your member will run a server process, another will run a client process, and then see if you can talk to each other over the internet. At that time, you'll face issues with the IP addresses, okay? And you'll have to resolve that. Shouldn't take you a long time, all right?
Okay.
It's just that you have to start working on it without worrying about it. If you worry too much, even without starting, then it will not get you anywhere, right? We know that. It has happened to me. It has happened to everyone.
Okay, thank you.
Yeah, you just have to start. And always start with the easy case, right? If you cannot solve a problem, convert the problem to something that you can solve, right? So the first thing would be to run both the server and the client on the same machine and see if they're working properly, then try to connect to different machines. Perhaps on the same network, you can use 2 different machines that are connected to your Wi-Fi. Then you can use the IP addresses provided by your access point. Once that works, then try to connect to 2 different Wi-Fi. One device is connected in this Wi-Fi, another device is connected to another Wi-Fi. See if that works. So go step by step and try to solve the problems, okay? And yeah, so yeah, by the time you are done with this connection, issues and everything, you'll get the project. Your group will get the project assigned. Implementing the logic for BitTorrent, it will take at most 30 minutes, I guess, if 5 people are working. Okay. All right. And some of you probably have a lot of experience. You can probably share that with other groups as well on the Discord channel. You can help each other for the connection setup. Okay. You can do that. Or you may also try to find some tutorial on the internet. Okay. If you want. Again, this is not a programming course, so I'm not going to teach you any programming. All right. It doesn't make any sense. Any other question? Anyone? We have 3 more minutes. None? Anyone? Let me look at the chat. Mhm. Mhm. Doesn't using a VPN hide what you are uploading from? Well, they will know about the VPN, right? And then the people who manage the VPN will figure out who is doing it. You cannot get away with anything that you do on the internet. People will find you. It's just a matter of time. If you are, dedicated to find someone doing something, you'll be able to figure that out. All right, then. If you don't
Almost.
question, then let's end it here. Okay, you can now disconnect. I'll probably do so as well. Thank you, everyone. Okay, I'll see you tomorrow. Yeah, take care.
Thanks, Professor. Have a good one.